Good evening, everyone. Uh, so now this is the next live doubt session for this course, MM18, Introduction to Crystal Elasticity and Crystal Plasticity. So we'll wait for some time. Some few people should join. Then we'll further continue. So good evening everyone. Here, as you see, no one is joining. So I'll just start my today's session. Okay. So welcome you all in this live session two of this course. So I'll move toward the further for question number one. The question number one is for an isotropic material, what is or are the number of independent elastic constants? So have we have already gone through videos. So based on that, we just can define this. E is equal to 2z bracket 1 plus h. Okay. And E is a Young's modulus and sorry, not h. This is mu. Okay, I'll just write down in presentation mode. Okay. Okay. So E is equal to 2z 1 plus mu. So E is a Young's modulus and G is a shear modulus. And another relation is E is equal to 2k 1 minus 2 mu. So there are in isotropic material there are two numbers of independent elastic constants. First one is this one and another one is this one. So answer will be option number 2. For the second questions, in second question, they're asking for isotropic materials, the directional elastic modulus is equal to. So here, directional elastic modulus E upon, sorry, 1 upon E, HKL value is equal to what? Is equal to S111 minus 2 S11 minus S12 in bracket, and this whole value will be in the another bracket, minus 1 by 2 S 4 4 bracket, and that will be multiplied with alpha value, alpha a square, b alpha square beta square minus alpha square, sorry, not minus, plus alpha square gamma square plus beta square gamma square. Okay, in bracket. So here if we'll uh, calculate these values, so in the end we'll get the value option number 4, this 1 by s11. Since the elastic modulus, it will be like we have to take a reciprocal, then it will become this value. Since these values will cancel out each other, okay, for isotropic materials, there will be everywhere the elastic modulus will be same uh, in isotropic material. If the elastic modulus is different along the three perpendicular direction, the material is. So first we have to check which in which the three directional there won't be three different elastic modulus in perpendicular directions. So we know there will be x, y, z, three direction will be there. If we'll take isotropic case, so if we'll make a, suppose we are making a cube. In isotropic case, every side, each and every side, all three directions, all perpendicular directions, there will be same elastic modulus since they are having isotropicity in nature, like that is containing isotropic tropicity. It means that elastic modulus will be same, and the direction in that direction, the atoms are present in that direction will be same. What about anisotropy? Yeah, it will be different. In anisotropy, there will be three directions, but here they are asking three perpendicular directions. In that case, anisotropy will having the same elastic modulus. But if we'll go in this direction, if we'll go in x direction 100 direction, either or 1010 direction or 001 direction, we'll get same elastic modulus. But if we'll go in another direction, then this will be different elastic modulus will get. So there will be different elastic modulus with different direction, but not in a perpendicular direction. In perpendicular direction, anisotropic also will say so. Uh, elastic modulus same. So these two answer won't be the correct answer. Then, if we see this orthotropic, in that orthotropic, in that the distance between this xyz axis, x g axis, the direction, the atom distance will won't be same, or molecule distance won't be same. So the crystal patterning will change. So there will be three different elastic modulus can contain in perpendicular direction of the crystal. So the answer will be orthotropic. What about monoclinic? It will be also having this two direction different, but one direction will be same. So the answer will be orthotropic. So here the question number 4 is a brittle materials has. So if we'll write down this stress strain curve, stress stress we are writing as a sigma, and this is strain. Okay. So strain is having the change in length upon total length. So it is a unitless value. Okay, and what about strain? Stress? It is a force upon area. So we have force Newton upon area. Area in whatever we can take nanometer square, nm square. Okay. So for brittle, like generally whatever elastic or plastic crystal will show, it will show like this region. Sorry. Okay. So till here we can say it is a elastic. After that, this part it is a plastic region, and this is elastic. Just remove this. This is elastic region. Okay. This part. Okay. This is plastic region. So in brittle materials, what is happening? This won't show any plasticity, plastic, plastic nature in that. Since we are applying the stress, then we are getting some strain, and there's a particular point, it will be like this. This brittle materials will break. Okay, brittle. So that's how it's not having it's having elastic zone, but not in plastic zone. It won't show any plastic zone. Now, what about large plastic zone? It is not at all showing the plastic zone, so there will be no plastic zone. Okay. So question number 5 is, in a composite body consisting of two different materials will be same in both. In a composite body consisting of two different materials will be same in both materials. So in composite body, we'll see what is the composite body first. Here you can see I'm just making a normal This is the core, and this is the matrix. This is the matrix. Then this is the pressure we are applying on this, force we are applying this. Okay, so here you can see we are taking a core, something like fiber, and this matrix is there, another material. So two different materials containing composite body we have taken, and the what will be the same for these two materials we have to tell. So we'll go for, first we'll see stress. If we'll apply the stress, force upon area, it will be the same for this matrix, because both are having uh, both. If we'll apply the force on area also, it will change simultaneously uh, according to the force. So stress will be same. So I'm sorry, actually the stress won't be same because area is different for both this area and this area. So area A1 and force we are applying same, but area A2, both are having different area, so stress won't be same. And what about strain? If we'll apply the strain, then the change in the length we have to measure compared to the change in the compared to the original length. So suppose we are having some length L. So here what is changing? If you are applying the strain, then the length will change for both at the same time for both materials. So here the answer will be this strain, since the changing in the length will be same for both. Okay, so this also won't be, and this also won't be correct. So only the option number 2 will be correct. Then again here the question number 6. The question is uh, 200 into 100 into 50 mm steel block is subjected to a hydrostatic pressure of 10 megapascal. The Young's modulus and the Poisson's ratio of the material are 200 gigapascal and zero point 0.3 respectively, and the change in the volume of the block in mm cube is. So we have to check the change in the volume in mm cube. Okay, so for that we have to check the change in volume. Okay, so for that what we have to do, we have to check, this is our block, steel block. Okay, so this is the sigma x stress, sigma y, which I is writing down, sigma z. So what is happening? We are the applying the pressure. So a pressure is the given as here pressure as the pressure is given as 10 megapascal. Okay, so P, and we know 10 megapascal. So we know that pressure P is equal to sigma x, since we are applying from all side, sigma y, sigma z, z. So change in the pressure will be like this. Okay. So we have to given this pressure P, and change in the pressure. Okay, this is change in the pressure. Pressure change in the pressure we have given 10 megapascal, and we have given the Young's modulus E value, that is around 200 gigapascal, and they have given the alpha value also, Poisson's constant, Poisson's ratio, that is 0.3. Okay, so for changing the value, we can calculate through the simple formula, that is, since it is a block, so we'll apply the bulk modulus approach. So here, instead of this Young's modulus, we'll take it as a bulk modulus, and minus P upon del volume, change in volume upon volume. Okay. So here we'll write down this as a simplified manner. So it will be del V is equal to P del P del P upon B. So we'll get the value of del V, change in volume, and the answer will be 60 mm square, mm cube. Since it is a volume, so it will be in mm cube. Sorry, here I did one mistake. We have to calculate the B value. For B value, we have to choose this formula. A is equal to 3K 1 minus 2 mu, and whatever I am telling this alpha value, that is mu. Okay, so just write down this, so you will get the B value, and if you put the B value here in this formula, then you can get the del V value, change in volume for the block. Okay, now next question. So here, calculate the Young modulus for an iron crystal when tension is applied along a 1 to 2 direction. Here I'll write down this one cube. I'll draw this one cube. In that, this is the x-axis, this is the y-axis, and this is the z-axis. Okay, so here we'll write down whatever the value are given: 1 0 0 1 sorry 0 1 0, and this is the 0 0 1. Okay, and the direction the tension we have to calculate young modulus. We have to calculate the young modulus for this applied direction 1 to 2. So what is the direction? 1. In this direction it will be 2 and 2. So it will be here. Okay, this is the 1 to 2 direction. No, it's not 1 1 2 direction. Just a second. I'll just write down. Okay, so the direction will be like this. Okay, so this is the direction of 1 to 2. Okay, sorry. 1 2 2. Okay, so so here Iron, we know iron is having BCC crystal lattice, and we also know the Young modulus formula for this direction 1 by epsilon HKL is equal to S11 minus 2 S11 minus S12 minus 1 upon 2 S44. In this one it is in a bracket, okay, and here into alpha square beta square plus alpha square gamma square alpha square plus beta square gamma square. Okay, then here for iron the S11 value will be Pascal inverse. It is around 0.757 into 10 to the power minus 7, sorry 11, and S22 again it is in Pascal inverse. The value is minus 0.28 0.757 into 10 to the power minus 11. Here 0.28 into 10 to the power minus 11, and S44 is equal to 0.86 0.86 into 10 to the power minus 11. Okay, so this is the S1, S11, S12, and S144 values are there. Then what about this alpha beta value? For that you have to calculate the alpha value. Alpha is equal to cos A, the angle between x-axis direction and the direction whichever is given 1, 2, 2. So how we can calculate this alpha value? We can calculate using this formula. Sorry, using, sorry, this will take as alpha beta gamma, so it will be uh, theta phi chi will take. So A dot B is equal to mod A dot mod B cos theta. This is the formula for getting this cos theta value, that is equal to alpha. And what about beta? Beta is y and 1 to 2 directions angle. Okay. Then what about gamma? Gamma is z and 1 to 2 direction angle. Okay. So we can calculate through this formula this alpha beta gamma values, and S1 S1 2 and S4 4 values are given here. We'll keep here and we'll get the Young's modulus uh, for this iron crystal, that is BCC. So the answer will be this one, option number 4. After calculating after putting in the formula and calculating the values. Okay. Now, okay. So now uh, here the question is, consider a thin wall tube capped at each end and loaded under internal pressure. Calculate the ratio of the axial strain to the hoop strain, assuming that the deformation is elastic. Assume that A is equal to 107 psi and Poisson's ratio is equal to 1 by 3, that is 0.33. Okay. So here there will be two, since we are taking a thin wall tube, so it will be like thin wall tube we are taking. So this side we'll say this is longitudinal direction, longitudinal direction, and the stress will be longitudinal direction, or stress will be axial stress. Okay. What about this side? This won't be axial, this will be circumferential. potential stress. And that is called this the stress will called hoop stress. Okay, so here the we have to calculate the ratio of axial strain to the hoop strain. For that, there will be two kinds of forces along with the tube. First one will be two kinds of forces. Two kind of forces will be there. Okay. First one. First one will be forces applied. Forces. Sorry. First force will be force due to applied pressure equal to force resisted by the cylinder walls. Okay. So first force will be an applied pressure and this in a applied pressure and for due to the applied pressure the force resisted by the cylinder wall. Okay, this wall. So that is we can say that force will be equal to P pressure into sorry pi by 4 d t square, and that is this pressure due to applied pressure is equal to force resisted by the cylinder walls. So walls will be there. So sigma, that will be the stress, sigma y, and into pi dt. Okay, so this will be this equal to this. Okay, and the second force will be along the along the radial direction of the tube. Sorry, radial direction of the tube. So that force will be P into I into dt, sigma x into 2 into 1 into t. Okay. So according to that, we'll calculate the value of first here we'll calculate the sigma y value. That is P d pdt upon 4t. Okay. Okay. That is here I forgot the value of t. Okay. And and the sigma x will be equal to p d t upon 2t. Okay, okay, it was here, not here. The t, this t is into it this side. Okay, so it will become like this. So sigma y, it is a stress, it is in this direction, y direction, and x direction it is an hoop strain. Okay, so if we'll take a ratio of the those two, we'll get the value, that is the ratio of axial strain and hoop strain. So that is around, if we calculate the all the values, then we'll get this value, these things, and the answer will be option number 2, 0.2. Now question number 9. Okay, so for question number 9, the question is pressure P affects the C by A ratio of hexagonal crystals. Write an expression for d C by A upon dP in terms of the elastic constant and C by A. Assume that the sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to minus P. So for this question, we have to calculate the value of expression of this. We have to write down the expression of C by A upon dP. Okay, so for that, first we'll write down the expression. What will be the expression for D? I'll write down here, C by A is equal to ADC by minus CDA upon A square. Okay, that is equal to, if we'll take both C common here, so C by A and A will cancel out. Okay, here AD will be there. Okay, so here inside it will be C by DC by C minus C is common here, and here what is that, dA upon A will be inside. Okay, so with this expression, these things we can calculate as a C by A D strain, that is epsilon 3 minus D epsilon 1. Okay, sorry. So how we can calculate this epsilon 3 and epsilon 1? For that, since here it is given that minus p is equal to these things, so we'll just write sigma p is equal to minus dp. Okay, since these things are given already, sigma 1, sigma 2, sigma 3, and minus p. If we'll take a sigma of this, either this sigma 2, so it will become a minus d sigma p. Okay, so I'll write this one, and after that, what about this sigma, the epsilon 1? For that we can calculate through this formula that is already we have seen in previous classes. Sigma 1 2, sigma 2, sigma 1 3, sigma 3, sorry, S, whatever I'm writing, S11 sigma 1 plus S12 sigma 2 plus S13 sigma 3. Okay, so after this, what will happen here? If we'll take, assume this values, we'll take a del value of these things, then we'll get the value of S11 plus S12 plus S13 whole of this dp, and value is in since the value is in negative here, so we'll keep the value negative. Okay, for same for sigma 3 also we'll calculate. So it will be uh, S13 sigma 1, S13 sigma 2, and the last one is S33 sigma 3. And if we'll calculate this also same, so we'll get the last value, the final value, it will be 2 S13 plus S33. Okay, after this equation, so dc by a is equal to what? It will be minus c by a. After putting these values here in this formula, we'll get a negative sign both from both places. After this calculating, they will get this c by a as 13 as a positive, then 33 as a positive, then negative as 11 and negative as 12. Okay, so the final answer will be, option number 1. Okay, here the question number 10. The question is, a cubic crystal is loaded with a tensile stress of 3 megapascal applied along the 110 direction, and find the shear stress on the 111 plane in the 101 direction. Okay, so here you can see Okay, here you can see. I'll just write the plane 1 1 1 here. I'll draw. This is the plane 1 1 1, and the given applied this tensile stress is 3 megapascal is applied around in the direction of 1 1 0. So this direction they have applied from here. This, so 1 1 0 direction they have applied 3 megapascal tensile stress. Okay, and they're asking find the shear stress on the 1 1 1 plane in the 1 0 1 direction. So 1 0 1 direction in this sense, this direction. Okay, this direction. Okay, 1 0 1 direction. So the normal force of shear stress will be force into cos lambda. Okay, whatever is the force in this direction, stress direction, into cos lambda, and the area of the stress, sorry, shear stress it will be A by cos theta. Okay, so the shear strain, shear strain, sorry, shear stress will be what? Shear stress HKL is equal to Fs upon As. Okay, so that is around F upon A cos into cos phi, sorry, theta, cos theta. Okay, now how we can calculate this cos lambda and cos theta? So for that, there will be the angle between. So applied stress direction is what? Applied stress direction is 1 0 0, and the plane is 1 0 1 1 1, and the shear stress direction whichever we have to find, this is 1 0 1. Okay, so cos theta, sorry, cos lambda is equal to the angle between the plane 1 1 1 and the direction 1 1 0. Okay, so so for that we can calculate the cos uh, lambda using this formula: A dot B equal to A mod A dot mod B cos lambda. Okay, and what about theta? Theta also you can find out like this. The theta is the angle between this plane, 1 1 1 plane, and okay, 1 1 1 plane. So here, so we can calculate this cost lambda using this plane and this direction of applied uh, tensile stress, and cos theta we can calculate using this plane, 1 1 1 plane, and 1 0 1, which side we have to calculate the stress value, stress, sorry, shear stress. That side we'll calculate this theta value, cos theta, and we can put this values in this formula and we'll get the shear stress value. So the option here is option number 1, 1.22 may. So the answer is here 1.22 megapascal. Okay. So now we'll move toward the further this question number 12. In that they are asking us a steel bar is loaded axially with a load magnitude of 100 Newton As shown in figure below, what is the strain energy stored in the bar? Assume E is equal to 210 gigapascal. Okay, so for strain energy, direct formula is there. Strain energy is equal to U, we are calling that strain energy. U is equal to sigma square upon 2. Okay, and strain energy here, the sigma value what is given, 100 newton. The steel bar loaded axially with a load magnitude of 100 newton. So sigma is what? Force upon area. So area what is there? 0.1 mm. Okay, this is the area. Area how will calculate? This value and this value. We'll just multiply, then we'll get the area. So 0.1 mm into 0.1 mm will get uh, sorry, not 0.1 mm, 0.1 centimeter into 0.1 centimeter, and force will be 100 newton. So we'll get 100 upon 0.1 into 0.1 whole square, the value, and 2, and E value what is that? E modulus, Young's modulus 210 Z P small a. Okay, so that's how you, after calculating this, you will get the answer. Option number 1, 3.8 into 10 to the power minus 4 Newton per meter. And the question number 13. Here the formula is straightforward. We have to give, sorry, here the question is a hydrostatic compressive stress applied to a material with cubic symmetry results in a dilation of minus 3 into 10 to the power minus 5. Something is missing here. The multiply option. Here the multiplication is there. 3 minus 3 into 10 to the power minus 5, and the three independent elastic constants for a molecules are C11 is equal to 50 gigapascal, and C12 is equal to 40 gigapascal, and C13 is equal to 40 gigapascal. Compute the applied hydrostatic stress that we have to compute. Okay, so dilation is what? Dilation dilation is equal to epsilon V is equal to epsilon 1 plus epsilon 2 plus something. What does that mean? It means that strength dilation. So the value is around minus 3 into 10 to the power minus 5. Okay, no unitless value. And after that, so what will be the E1? E1 will be, since these three values are equal, so how will calculate this EV? So EV will calculate EV upon 3. Okay, and the issue, here again, this E1 is equal to EV by 3, so E2 also will be equal to this. sorry, epsilon 2 is equal to this value also equal to E2. Okay, and we know that the hysteris, hydrostatic stress sigma is equal to sigma ij is equal to c ij epsilon ij plus the summation of this. Okay, so here we have three values: C11 epsilon 1, C12 epsilon 2, C13 epsilon 3. Okay, if we'll keep these values, so we'll get the value of C. Okay, I. So we'll get the I value. C1 value will get, and that if we'll keep these values here, C11 value, C12 value, C13 value, and also the epsilon value, epsilon 1, 2, 3, then we'll get the answer as sigma 1, that is equal to option number 1 minus 1.3 megapascal. Okay, now the option number 14, here the value of E and V of niobium. Okay, E is a Young's modulus and V is a um, Poisson's value. Okay, so for niobium are given as 150 gigapascal and 0.34. Okay, compute Sear modules. So Sear modules formula is, it is very simple formula. E is equal to 2. The relation between Young's modulus and Sear modulus is like this: G 1 plus V. Okay, so G value we have to calculate. For that we have to take this E like this and 2 1 plus V. Okay, so the option number 1 will be correct answer. Okay, after putting this E value and V value, we'll get the answer of 55.97 GP. So the last question here: in a circuit box, a copper rod at room temperature of 25 degrees centigrade has a gap of 0.3 mm between the end of the rod Q and the rigid wall. If temperature of the rod increases to 70 degrees centigrade, then what is the compressive stress acting on the rod PQ? Assume the Young's modulus is this one and alpha value is this one. Young's modulus is 100 gigapascal and alpha value is around 15 into 10 to the power minus 6. Okay, so here first we have to find the elongation. So first the temperature was 25 degree and the gap elongation is around 0.3 mm, 300 mm. Okay, so that time the gap between these two, it was around 300 mm. Okay, and if temperature of the rod increased to 70 degree, it means the filer Tf is equal to 70 degree, and Ti is equal to 25 degree. Then what is the compressive stress acting on the rod PQ? We have given Young's modulus E value, 100 GPa, and alpha value is also given here. It is around 15 into 10 to the power minus 6. So here, first we have to find the elongation of the first things. We have to find the elongation of rod. Okay. Then second thing, we have to see first elongation is happening, then less than gap. When elongation is happening, the gap between this rod Q and the wall will be less. And when compression is happening, then the elongation, this compression is more. Sorry, compression. Then the gap, compressive stress of the bar of the rod, elongation restricted, and elongation due to the thermal expansion gap. Elongation gap is more than elongation restricted. Okay, so here the gap is 0.071 mm. So sorry, here the gap is the 0.3 mm. So compressive strain after the elongation of rod, we have to find out the compression strain. Strain. First, we have to find out the compressive strain. That is epsilon. That will be equal to restriction, elongation restriction upon total length. Upon total length. Okay. So after that, we will write the sigma of compressive stress, that is equal to Young's modulus into epsilon, epsilon c. That is compressive strain. Okay. So that's how we can calculate the sigma c value, like compressive stress value. Okay. I'm having some doubt here, so I'll clarify in the next session for you this alpha value and how to calculate these things. Okay. So now I'll wind up the session. So far we have completed all the questions. Thank you for joining. Thank you. Thank you for watching.